Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is his first day of a one-month visit to MSR, where he'll collaborate with Wolfram and me and other folks on runtime verification of concurrent systems. So started as a professor at Koç University in Istanbul, Turkey. Before that, he was at Compact Circ, and before that, he was at Berkeley. Welcome, please.
Thanks. Good morning. I'm here to tell you about the VYRD project, which concerns detecting concurrency errors in data structure implementations through runtime refinement checking. This is joint work with my student Tayfun Elmas and Shaz and others at Microsoft Research. The problem we're addressing with this work is as follows. We're given a specification for a data structure, a high-level executable specification. This spec has atomic operations, and we're given an implementation that's concurrent and not necessarily atomic, linearizable, and it may have race conditions. And the idealistic goal is to verify that all executions of this implementation are consistent with the spec. Practically, what we're after is catching errors due to concurrency in the implementation. And we're going about this using runtime verification, mostly because exhaustive verification of refinement for the systems we're looking at is just too complex, either computationally too expensive, or it requires a lot of manual effort by a verification expert. And this is difficult to do for complex multi-threaded data structure implementations. So by doing runtime refinement checking, we're giving up exhaustiveness, but we're still doing something more thorough than simple testing. As we see, we'll define different notions of refinement, and each of them will be a different correctness criterion for a multi-threaded test. And we'll see that we're more likely to catch bugs in this fashion than pure testing. As an appetizer, before I dive into the more technical parts of the talk, here's a bug that we caught in an actual file system. It's called a scan file system, was implemented on Windows NT. And this is an error during which data loss occurred because of a concurrency error. And we'll see that this would have been difficult to catch via testing. This file system, like many others, it writes back, it has a cache for performance improvement, and it writes back dirty blocks in cache periodically back onto the disk. And in the bug scenario, here's what happens. There's a dirty cache block, B. It's put into a queue, to the right queue, to be scheduled to be written onto the disk. And the file system gets around to writing this queue back onto the disk. The disk write starts and finishes. Meantime, the block is still marked dirty. Before the file system gets around to marking B clean as having been written onto the disk, a thread switch occurs. And in the meantime, a new data gets written to this block. And then, again, a thread switch occurs. The file system marks B clean, thinking it just copied it onto the disk. As a result, a block that's really dirty is marked clean. This is a difficult bug to catch through testing because further read calls to B will hit in the file system cache until that block is evicted from the cache. So if you'd like to catch this error through testing, you must not issue further writes to B, issue enough other requests to the cache so that this block gets evicted, and then issue a read to B. And this whole testing scenario is unlikely to occur during random testing, whereas, as we'll see in a little bit, through runtime refinement checking, it gets detected immediately. Okay, so with this, here's the outline of my talk. I'm going to give a few preliminaries so that I can describe things precisely. I'm going to define a notion of refinement that we call I/O refinement, illustrated on simple multiset example. I'll talk about how we check I/O refinement at runtime. And then I'll talk about an improvement to IO refinement that adds more observability. Then I'll talk about how we applied this to a few systems, including the Boxwood Project from Microsoft Research, Silicon Valley. And then I'll point to a few directions of future work and collaboration here at Microsoft. So preliminaries, very quickly. The data structure implementation has public methods which correspond to data structure operations. And the application threads issue public method calls concurrently. And they have the illusion that calls from all threads are executed atomically in some linear order. The semantics of programs, specifications and implementations, we take as state transition systems. And again, very quickly and informally, you have a set of program variables, a set of program states, each of which is an assignment of values to variables. And you have a transition function that makes state evolve over time. Given a current state and an action performed, it specifies the next state that you will go to. And we separate actions into two categories, the ones that are visible, such as method calls and returns, and maybe some others. And the invisible ones, which are not going to be part of traces, as we'll see. And these are, for instance, updates to method local variables. Okay. We distinguish call actions and return actions as tuples. Each of them has the thread ID. It says call and return, and the method name. And the call action has the list of arguments, and the return action has the return values as part of it. With this, a run of an implementation or a specification is a sequence of state transitions, each of them labeled by an action. The red ones in this sequence are the visible ones. So the trace corresponding to this run is then just a sequence of visible actions that you observe along this run. We defined a well-formed atomic trace as a trace in which between a matching call and return, there are no actions by other threads or by other methods. Okay. And a well-formed atomic trace consists of these atomic fragments that start with a call action and ends with a return action. And the call action and return action we call the fragment signature. And we use this to define determinism for state transition systems. We say such a state transition system is deterministic if, given a fragment signature, an initial state, then if this atomic fragment implies the same final state. In other words, if you start from a given initial state, execute an atomic fragment with a given signature, if there's only one next state you can go to, then the system is deterministic. I should remind you that return actions contain return values. So this doesn't mean given a method call there's only one return value. It just means given the call and the return value there's one defined next state. Yes?
Maybe this was in the previous slide. Can other threads be produced in the call and return?
No, not in a well-formed atomic trace, but in a regular trace, yes. We'll see that I'll require specs to have well-formed atomic traces, but not implementations.
Then actually, can you go to the next one? The one with determinism. So now, when you say that atomic state is deterministic, you're also not worried about introducing to the middle.
No. So, in fact, this definition is only for specifications. Okay. Just as a preview, sometimes when people don't like to write specifications, we'll suggest that an atomic version of the implementation will serve as the specification. And I'll get back to this point in a little bit. So with these preliminaries, here's how we define refinement. You have S, a state transition system for the specification. It's required to be to have well-formed atomic traces. You have the implementation state transition system, and refinement in words says projection of traces, visible actions, to application threads match in the implementation and the spec. In other words, you say I refines S if for every trace of the implementation there's a trace of the specification, so that for each application thread the projection of the implementation trace and the projection of the specification trace to T are the same. And defining different actions as visible will give us different notions of refinement, as we'll see in a moment. And hopefully this picture will make refinement a little bit more intuitive. In the implementation, you have each different color here is a different thread, different method call. And actions performed by these are possibly interleaved. For this implementation trace tau I, we look for a specification trace tau S, which is well-formed and atomic. And it has the, for each thread, it has the same sequence of visible actions. I/O refinement, the simplest notion of refinement we're going to define, says only call and return actions are visible. In other words, what we check is that there's, for each sequence of calls and returns in the implementation, there's a spec run, well-formed and atomic, with matching call and return values. Since the specification is atomic and deterministic, the spec run will give us a linear order of method executions that we refer to as the witness interleaving. And if we were given this witness interleaving, it would be straightforward to check whether for a particular trace refinement holds or not. Of course, the practical issue is that there are too many possible interleavings. And what we do for runtime refinement checking is to infer a witness interleaving from the actual implementation run. And the way we do this is by defining an action in the lifetime of a method as the commit action. I'll give a little bit more intuition about what this commit action is in a moment. But the idea is by observing the implementation trace and the ordering of the commit actions, red, green, blue in this case, we infer that the witness interleaving is supposed to be the red method call, the green method call, and the blue method call. And then we check that the call and return values match in the two executions. Here's a bit of intuition about the commit action. The idea is that the ordering of commit actions is supposed to give you the application thread's view of the ordering of data structure operations. Again, practically this translates to marking a line of code in the method body, or possibly several lines. The first line of code that makes visible to other threads the modified view of the data structure. You can see marking commit actions as an aid in constructing an abstraction map from the implementation to the spec. And practically, again, what this translates to is for the programmer to annotate the code in several lines to indicate the commit points of methods. Before I tell you how we check I/O refinement and other, yes?
So I should think about this as the programmer inserting, say, like a commit action or something like that inside each transaction.
Mm-hmm.
Now, well, there could be problems like, for instance, what if two such actions execute within one method, or maybe under some execution, maybe no such commit action execute. So don't you have to have well-formedness on how you can put that?
Right. So typically it won't be one line. It will be several lines in your code which are commit points under different circumstances. And ideally, we're going to see that we record actions of the implementation in a log, and there should be one commit action per call. If that's not the case, then it's the programmer's job to fix it. And but we don't do any static checking to guarantee it. We just fix it if it occurs during runtime. So to illustrate some of the concepts and the checking methodology, here is a simple example of a data structure, a multiset. It only has two operations, insert pair xy. The intent here is to insert integers x and y into the multiset if this operation succeeds. Sometimes it can fail, in which case the state of the multiset should remain unmodified. Okay, and then there's one observer method, one lookup operation, and it returns true if and only if the integer x is in the multiset. The implementation of the multiset is going to be based on an array. It will have a content field where we insert the integers, and it will also have what we call the valid bit, to indicate whether, for instance, the third element in the array should be considered part of the multiset or not. Yes?
When you say insert pair, you mean insert two elements of multiset or one pair?
Oh, two elements. It's two unordered integers x and y, and it's intended to be interesting because it could be that one of them looks inserted and the other one isn't, and tricky scenarios can arise because of that. Okay, so the implementation uses a helper method called findSlot. You give it an integer and it looks in the array to see if there's a place where it can put it. And it does this by going through the array in order. It acquires the lock for the ith location, li, and if there's nothing there, it inserts the integer there and returns the index where it inserted the integer. Otherwise, if it goes through the entire loop without finding a location for the integer, it just says, I haven't found a place, 0. Okay. And the implementation uses findSlot as a subroutine and works like this. It first looks for a slot for the first integer. If it can't find one, it just returns failure. Otherwise, it looks for a slot for the second integer. If it can't find one, it erases the first number that it wrote and then returns failure. Otherwise, if you get to this point in the code, it means you found slots for both integers, in which case you acquire the locks for the ith and the jth location and set the valid bits for both locations. You release them and you return success. And the same idea is shown in pictures here. The green check mark means the valid bit is set. Okay. A lookup goes through the array again in sequence. It acquires the lock, and if it finds an entry with the valid bit set and the content matching the number it's looking for, it returns true. Otherwise, if it goes through the entire array without finding this, then it returns false. The spec is very simple. Let me start with lookup. It just says true if and only if the number is in the multiset. The insert pair spec upfront decides whether insert is going to succeed or fail non-deterministically. And depending on that decision, it either inserts the two integers into the multiset, otherwise it doesn't, and it just returns this status at the end. In a little bit, we'll see why this way of doing things makes things easier for us. Okay, so how do you mark the commit action in, say, the insert pair method here? The idea is, again, to find the first line in code where the modified view of the data structure state is visible to other threads. And in this case, it happens to be when you release the first lock right here. Okay. And if you, let's go back and look at what lookup does. It goes through the array in sequence, acquires locks, checks if the number is there, and returns. So if we think about the ith location, for instance, for a lookup method to see integer x as in the multiset, it needs to be either interleaved before the lock is acquired or after it's released. And if it gets interleaved here, the lookup will return false. If it gets interleaved here, it will return true. A similar argument holds for the jth location. So at this point in the code, any other methods that get interleaved before commit will see insert pair as not having taken place. In other words, they will see x and y as not being in the multiset. And after here, they'll see x and y as being in the multiset. Wrong? Okay, so how do we check IO refinement then? We look at the implementation trace. I'll tell you in a few slides that we actually do this offline using a log. But just for illustration purposes right now, imagine that we can see all of the implementation trace at the get-go.
So I have a question in the previous slide.
This one?
Yeah. So what does the programmer mark the release? At that point in the code, he just adds commit to it, or is commit and annotation just added to a line, or?
To a line, yes. So the actual release of the lock and the commit point need to be atomic. I'll get to that point in the picture also again. We look at the implementation trace. And remember, I/O refinement checking says only call and return actions are visible, so everything else is marked epsilon as an invisible action. And when we encounter a commit point, it means that method is the next one that should be executed in the specification. So we look at the implementation trace in increasing time. As we see a commit point, we look at the call and return values of the method that just committed. And then we tell the specification to execute its version of that method with this call and return value and to go to the next state. Okay, and we keep doing this. And if you remember that the spec is atomic and deterministic, there's at most one run for a given sequence of method calls and return values. And the spec method is written in such a way that given the call and return values, it just updates the state. And if it fails, if it's not possible to do that. So then runtime checking of I/O refinement proceeds in this way, and if at any point the spec is not able to update the state for the given return value, then it signals an error. Of course, a refinement check done in this fashion could fail either because the implementation is really wrong, or you just selected the commit points wrong. And because along with the implementation trace, you have a specification trace, or say the applications view of the trace to look at. By inspection, you can tell which one of these is the case, and you either fix how you define your commit points, or you fix your implementation. And even this simple notion of refinement improves simple testing, because if you imagine that you have a multi-threaded test without witness interleaving, without linearization of method calls, you don't know what return values are correct and what return values are not correct. So you have to either consider all interleavings, or you have to say something conservative about under legal interleavings, such and such return values are okay.
So do you give the specs for the epsilon operators as well, or is that?
No. What I mean in this picture is this is actually not going to be in the log. I'm just trying to show that other stuff is happening, but it's not visible. A commit action, for instance, if you look at this example, a commit action is the release of a lock. And in I/O refinement, I said only call and return actions are visible. So I just wanted a box to show where the commit is happening. So to do runtime refinement checking without having too much concurrency impact on overhead on the implementation, we actually, during runtime, only write relevant actions into a log. And verification runs as a separate thread. It only reads actions from the log and does not interact with the implementation in any other way. And the log is simply a sequence of visible actions and commit actions. And you're required to ensure that the actions appear in the log in the order they actually occur in the implementation. In other words, you must perform an action atomically with the corresponding log entry. The way we keep the log, part of the log is in memory. So although logged actions of the implementation are serialized, there is very low impact due to contention, because all you're doing is inserting one pointer or one object reference at the end of the log. Yes?
Doesn't the contention for the log file force, a due set of behaviors in the implementation?
Well, I mean, some serialization happens, and this of course, yes, affects the implementation some. But since you're trying to acquire the lock for the log and just write one object reference there and then you release it, relatively speaking, the impact is low.
I think the work that is done during one log acquire and log release is very small. It's like flipping a pointer.
Of course, this depends on at what level of granularity you're doing the logging, and we'll see that in a moment also. Okay, so how does an error show up then? Suppose we break the find slot implementation. Instead of the find slot acquiring the lock before it checks, it acquires the lock after checking that the content is null. So it's possible that two concurrent insert pair operations both think the ith location is available for them, and they're going to overwrite each other. So here's thread 1, it's inserting integers 5 and 7 into an empty multiset. Here's thread 2 inserting 6 and 8. And in the very beginning, they read A1's content as null. I think they can go ahead and insert there. After insert pair 5, 7 writes 5 and 7 into the content area, but before it sets the valid bits, thread 2 comes along and knocks out 5 from the first location. It overwrites it. And then this method finishes. And if you just simply checked, are the numbers I inserted really in the multiset or not, you'd see that 5 is actually not there, but 7 is. And later on, thread 2 inserts 6 and 8, and at the very end, instead of 5, 6, 7, 8 all being in the multiset, you only have 3 numbers. And if you did some lookups after this one finishes also, you'd see that 6 and 8 are there, but 5 actually isn't. Here's a possibly more interesting case where thread 2 again thinks it can write into the first location, but doesn't do so until thread 1 finishes. So thread 1 does its work. It checks if 5 and 7 are in the multiset, everything looks all right. And then thread 2 again knocks out 5 from the first location and inserts 6 and 8. At the end, you have 6, 7, and 8 in your multiset. And then you check if 6 and 8 are in the multiset. Again, everything looks all right because they're in the multiset. But if you had done a lookup of 5 at this point, you'd see that it's actually false. You've undone the work that another concurrent thread did.
Why is this more interesting than the previous one?
Because if I had written a multi-threaded test, I would probably say, okay, I did an insert, and then I'd again put. And since I don't have a delete operation, I know that after I insert something, it should be there. I would do an insert pair of 5, 7, and then I would check are 5 and 7 there. It would say okay, and then in thread 2 I would insert 6 and 8, and it would say they're there. But at the end, the actual state is wrong.
But didn't a similar thing happen in the previous one? You inserted 7, right, but it wasn't there.
But when you do the lookup of 5, it fails already.
Ah, okay.
It's a local, what you're saying is this is less interesting because it's locally you would know, detect a test would detect that something was...
Okay, I take it back. It's not more interesting. They're equally interesting. Okay, so there's already a hint that simply doing lookups or method calls that the data structure makes available might not be a thorough enough way to test your data structure. So to improve that case, we add more observability into the test by defining a different notion of refinement. Again, the idea here is that the test programs you've written may not be performing enough observations or frequent enough observations. You might think you could fix this by inserting more of them, but then you'd affect the concurrency of the implementation too much, and the observations may not get interleaved in the interesting points that you'd like them. For instance, in the extreme case that you have a test program that does no lookups in the multiset, you'd never detect anything. Again, let me try to motivate this a little further. Now, suppose that I added a remove operation into the multiset, okay? And suppose that my implementation is broken, so that I do an insert pair of AA, the same number twice, but the implementation only inserts it once, okay? So if I was just doing simple testing or IO refinement checking, the only way I could observe an error would be if it showed up in the return value of a lookup of A. So I'd need an execution that first inserts A and A, and then later on removes it without doing any A-related things, and then looks up A. Okay, this is the only way that it would show up through testing. And this is a difficult scenario to hit just through random testing. But you'd be much more likely to detect this error if you actually looked deeper into the data structure state right when insert pair AA commits. Okay. And to add this more observability, what we do is to define a correspondence between the states of the implementation and the spec. Okay. But how should we define such a state correspondence? Simply saying that the states should be equal does not really work. For instance, here are three examples of three examples of multiset state in which the elements 1, 2, and 3 are in the multiset, 4 isn't. Okay. In this one, there are arrays, but the numbers are ordered differently. And this is a binary tree implementation where there's an indexing structure on top. But if you think of what's really just in the data structure or not, you should just think that 1, 2, and 3 are in the set. Okay. So intuitively, you want to capture the idea that at this point and in the execution, all lookups to this state or to this state or to this state should return the same result. And you're trying to abstract away spec or implementation state that is not part of the abstract data structure state. In other words, you're trying to come up with a canonical representation of the relevant part of state. And we call this view. Okay. So both the implementation and the specification define this auxiliary variable called view. And what it does is to capture the canonical, it canonically represents the relevant part of the state. Both the spec and the implementation have their copy, and the user must indicate how view gets updated in the spec and the implementation. So they start initialized to the same value, for instance, the empty multiset. And in the spec, view needs to be updated once atomically between the call and return. In the implementation, again, hypothetically speaking, it's updated once, and then again atomically with the commit action. And then what we do is that for corresponding methods, views match at the commit point. Or more formally speaking, we now declare the view computation as a visible action between the call and the return, and we say that it happens atomically at the commit point. So in addition to the call and return values, now we have this action labeled with some view, some representation of the state, and we require that the two match in the implementation and the specification. Yes?
But if the matching of the views happens at the commit point, what does the implementation really do between the time the commit happens and the return happens?
Okay, good observation. The computation of view actually could be looking ahead in the log, because I have the log, and I might be doing some more bookkeeping work after the commit action, etc. I might ignore certain modifications done by other threads. So that's what I mean is the implementation is doing bookkeeping or wrapping up. That is not really changing the abstract view of the data structure state, but maybe fixing up the indexing structure or reorganizing things so that things happen more efficiently, etc.
The follow-up question is, what will happen if the view is checked actually at the return point instead? Is that the same or is it different? Well, because in the middle, other threads could have intervened and started changing the state again.
So in terms of how I formulate the refinement check, here it doesn't really matter if you say, if I annotate the return action with view or the commit action with view. Yes?
I don't understand. I see how you can compute a view at a commit point in the implementation. But in the specification, I thought that you're given the call and return, and you just compute the final state. Mm-hmm. So I don't see where the intermediate state is in between the two that you can... Okay,
there isn't really intermediate state. What I mean is, suppose in the specification you did the insert operation. Maybe you inserted...
No, that's the spec of the multi-set insert.
Well, in the multi-set spec, that's a trivial case because the spec state is... We need all of the spec state. But suppose somebody wrote you a spec in the form of a binary tree, and then you need to abstract away some stuff.
Sure.
In that case, the abstraction is the view computation, but there is really no intermediate state. It's just you're getting rid of the indexing structure. To finish up my answer to Shriram's question, maybe I should answer it after I show you this slide. So in the multiset example, for the implementation, this is how you define view. And it might look a little counterintuitive at first. I guess this part is valid, is intuitive enough. You say, start with an empty view and put all the entries which are marked valid. Okay, and that's what we tried at first, but it didn't work. And after some iteration, we arrived at this definition of view. We say include into the view the elements if they're marked valid, or if their lock OK variable computes to true. And you say, well, okay, is the lock held by any thread, or is it held by the thread currently committing, or is it held by a thread executing a lookup? In that case, you declare lock OK true, and then include that into the content. Okay, you can imagine that, for instance, if I didn't have this clause here, suppose there are several lookup threads executing, and they each hold different locks for different array entries. If I didn't have this one, they would get ignored by the excuse me, by this view computation. So I guess my point here is the view computation sometimes might have dirty or tricky parts. But basically, it's trying to, at the commit point, define what the data structure state visible to other threads should be. And because I have the entire log at my disposal, I might choose to look ahead a little bit in the log and include some future foresight or prophecy into my view computation. Okay. And when I say the view is computed atomically with the commit action, what I actually mean is you're doing this offline. You look forward and backward in the log, you compute this, and then you say, okay, here's the view action, here's its label, and then you perform this check. Yes?
I don't understand what view exactly is. So in the case of a binary tree, the view is a sequence of the leaves?
Yes, the sequence of the leaves that are marked valid, let's say. But
sequence in any which sequence? What order?
Well, it depends. If it's a binary search tree, if the leaves are supposed to go from low to high, you just say traverse the leaves from left to right, include the valid ones. If you have an unsorted array like this, because in the end you simply want to do an equality comparison, you put in the ones marked valid, and then you sort the lists, and then you say this is the view.
I see. So in the case of multiset, it's not completely trivial. So you have to sort.
Yes.
So the sorted array will uniquely
match. Or you can say the views have to match modulo sorting. It's the same. Yes.
How do you know that you've dumped enough stuff in the log to be able to calculate, like that view you just showed,
okay.
The implementation?
Good question.
I mean, I'm going to have to dump into the log.
You have to log all the variable updates that factor into view. I mean, you look at the code, anything you're referring to in view, you have to log it. Okay, so you're getting more detailed checking, but there's a price to pay. You have to log more stuff. And you may also have to log lock acquisitions and releases. I mean, these may not even look like data structure or method local variable updates, but to define view, like I did here, for instance, you have to log those also. And of course, you have to make sure that your log doesn't reorder things, that they occur in the log in the order they occur in the implementation. So you're incurring more overhead, and you're affecting concurrency a little bit more, but you're doing more detailed checking. But the programs we're looking at, and in particular Boxwood, does a whole bunch of logging for recovery purposes anyway. It's meant to be reliable. If a machine crashes, it needs to read over the log and reconstruct its state. So it's already sacrificing some performance to keep logs, and so we figure what we're doing could also be tolerable. Okay, so I'll give you a quick run-through of what we've done implementation-wise. So first we worked on two multiset implementations. One was array-based, and the other one was binary search tree-based. And when I say we worked on, what I mean is my student worked on it. And it was an interesting exercise because we had a chance to use runtime refinement checking during development. So as he was writing code for the multiset implementations, he caught bugs in his implementation, methods that didn't work as he thought they should. He caught through this, and in fact he caught a bug in a paper that Shaz and I had submitted to a conference. Luckily before the final version got out. But and thinking about your program in terms of these commit points and defining a view just makes you understand it better and results in cleaner, better understood code. Earlier work that I had actually presented here about a year ago, had caught two bugs in a file system independently developed by other people. And but our real focus for the last couple of months has been the Boxwood System being developed at Microsoft Research Silicon Valley. And here the idea is exploring abstractions as storage infrastructure. So they have a B-link tree implementation built on top of another abstraction. The abstraction in the bottom just gives you segments named by UIDs, and on top of that they have several data structures implemented. And the B-link tree was one of the trickier ones. They implemented an algorithm due to Sajiv and others, a very highly concurrent implementation of a B-link tree. So B-link tree is very similar to a B tree. The idea is you want to get to your data through as few hops as possible. You want to have a bushy tree. In this variant, all data is in the leaves. The non-leaf nodes just form an indexing structure. And the leaves at the same level are linked from left to right. This allows a very highly concurrent algorithm where there are insertions, deletions, lookups that are all going on together, and they may overtake each other when they're locking and releasing nodes. And to make it even more interesting, there's a separate thread, a compression thread, that occasionally walks the data structure and rearranges it and makes it more balanced or better filled. So the way they're implementing it is actually there are B-link tree instances running on separate computers, and they talk to each other through this distributed locking mechanism, and they're all built on top of this UID abstraction. And in this case, we took as the spec the atomic version of the implementation. And what I mean by this is there's a single global lock, and the method must acquire the lock. A public method must acquire the lock to start. And when it's done with its work, it releases it in this way. Method executions are linearized. And the idea in taking this as the spec is saying, well, probably you got the implementation of the method right, but the concurrency is trickier and more error-prone. In other words, if you just use their implementation in this atomic mode, it would probably work correctly, but because of multi-threading and concurrency, it could break. Yes?
You can also say, of course, if you split the testing into two parts where you first
Sure.
test the linear code.
Right. I agree. And view, in this case, we defined as simply the data in the leaves ordered from left to right and traversed through these pointers. We implemented two different levels of granularity in the logging. In the fine logging version, we log every write to every tree node. And in the coarse mode, if a bunch of writes to tree nodes are protected by the same set of locks, we log them all at once as an atomic entry. I already defined view. There's one myth that I'm not sure I referred to in earlier slides, if you think about, for instance, this B-link tree as the entire state of a database, recomputing view by traversing the entire data structure for each method call is, of course, very expensive. So you'd like to do this incrementally. You'd like to just see what changes happened to view since the last commit point and do that at each commit point. So that's what we do, and that one's in place. So we have this whole thing implemented, and it very nicely catches hand-inserted bugs. But unfortunately, I don't have a glorious bug detection story to tell you. We have an implementation from about 10 months ago. And unfortunately for us, fortunately for them, it seems to work correctly. So we're right now exploring ways to stress test this implementation and see, for about 2 weeks we've been doing this, to see if we can catch any concurrency errors.
When you say stressing, you force more interleavings, is what you mean?
Some of that, some other tricks that I'll show on the next slide. But our real hope is when the Boxwood folks give us the new version in which the B-link tree module has a cache. And there's cache, log, and the B-link tree all interacting in tricky ways, and hopefully there are some bugs lurking in there. So ongoing work, just as Kiran predicted, is we're trying to force threads to switch more frequently randomly. So we're inserting artificial yields in the data structure implementation here and there. And we're randomly changing thread priorities before calls to yield. This is in the fashion of researchers at IBM or others. Yes?
Do you also look at weaker memory models? So what kind of memory models do you?
No, we don't. I mean, sequential consistency is what we assume. But the more interesting ongoing work that my student is doing as we speak is to explore all thread interleavings for a given fixed test case. And the idea is to run some test code, build a relatively complex tree, and then from then on issue a small number of threads, but explore all possible interleavings that could happen from that point on. So you can think of this as a constrained model checking run. And of course, it's only practical for small numbers of threads and small numbers of method calls per thread. But you could imagine that you have the B-link tree, you have an insert, delete, and the lookup, and the compress, all talking about the same data entry. And hopefully it would catch errors. And our advantage here is that the state graph of this constrained model checking run is a directed acyclic graph. So what we do is every time there's going to be a read or a write of a shared variable, a thread checks with a thread manager, and the thread manager tells the next thread to go on or to stop, in the fashion of Verisoft by Patrice Godefroy and others. The difference is, instead of checking invariance, we're checking refinement. So refinement checking is the invariant we're doing in this constrained model checking run. And future directions that I hope to explore while I'm here is to generalize and streamline this approach to see how instrumentation could be automated. The programmer should only mark the commit points, and if she wants to do more thorough checking, she defines view, and then we figure out what variables need to be logged, and we instrumentally program our object code to do the logging. And the verification is just automatic. The spec is again taken as the implementation with in atomic mode. And we want to see with the spec sharp folks here how we could use their stuff or they could use our stuff, vice versa. I want to investigate how to use a model checker not to verify a specification or an implementation, but to simply drive it to interesting interleaving. One idea I have on the side that some undergrad students are working on is to develop a visualization tool that allows you to navigate in these debug traces in the spec and the implementation in parallel, because in text mode this is really difficult. And future directions is to do the same thing for distributed software, or say maybe a bigger chunk of Boxwood. And here the idea I have is inspired by earlier cache coherence verification work I did, where for a distributed system, instead of a spec for the entire system, you have per node specifications, and you implement and verify the contract, the per node contract at each node at runtime. And the composition of the contract implements the overall high-level spec. This one you can check exhaustively using theorem proving or model checking. And again, here the motivation is that many of these distributed systems use caching or similar ideas for performance, and that makes it difficult to get the concurrency part right, as evidenced by hardware verification work from before. And Boxwood's chunk manager, let's see, this guy here that gives you the abstraction of segments named by UIDs is distributed and tricky, and we'll consider applying the distributed version of the VYRD project to this, or the cache version of the B-link tree. That's all I have to say. Thank you for your attention.
What languages are those examples written in?
The multiset is written in Java, Boxwood is written in C#, and the scan file system is written in C.
How do you present an error trace to the user? Because you did this checking at logging time at offline, so you don't have the complete implementation trace.
No, but you have the state that you reconstructed from, you report the view basically, the view at the last commit point, and the increments, the changes to the variables that happened since the last commit point, and then the user has to figure out from there. The visualization tool I just alluded to, the hope there is to click forward or backward in time and to be able to browse implementation or specification phase. And you can click forward in time in the spec, so execute a whole method, or you can click forward or backward in the implementation. So you do a variable write or undo a variable write, go forward or backward in time. But that one is really not in any shape to show you here.
When you say that the memory model you consider is sequential consistency, I mean, is the memory model not whatever memory model is used by the implementation of C# or Java that you're using?
I have to admit I haven't given that issue thought before, because our log forces us to serialize these writes and reads to shared variables, assuming sequential consistency works for us. But I should think further about more relaxed memory models.
Yes, because of course real memory models are weaker than sequential consistency.
Right, that could possibly, I mean, we could implement a log based on more loose memory models, and that could reduce contention for the log and maybe reduce the concurrency impact on the implementation. But Boxwood at least had a serial log like that, and was based on, at least, not at the language level, but at the UID and nodes level, it was based on implementing sequential consistency. So it worked for us. Thank you.